Hi, my name is Mark. This is for Exercise Science 250. My subject is recreational scuba diving, something I'm interested in, I've been certified in, and I'm going to talk about the physiological changes during scuba diving. Within my presentation, I'm going to talk about much of the changes, general changes that happen during scuba diving, things that you'll understand, as well as some of the challenges I've had, some of the limitations and delimitations to the research that I've seen, and some of the average percentages of change that our bodies go through while scuba diving. Now, our main variable is atmospheric pressure. And to understand atmospheric pressure, we first need to understand what we feel at the surface of the Earth at 1 atm or ATA. Atmospheres are atmospheres absolute. If you can picture a column of air reaching the entire height of our atmosphere, a 1 meter squared column of air, combined with the gravitational force of the Earth, this is the pressure we feel at sea level. And as we descend into the water, we double the atmosphere at about 10 meters or 33 feet, significantly less than the distance to the outer reaches of the atmosphere. We see in this picture with the balloon, at 1 atmosphere it's at its greatest volume. Go down to 2 atmospheres, we see that the volume has cut in half, and down all the way to 5 atmospheres, it's 1/5 of its original volume. Now within the water, the pressure in the water, we call this hydrostatic pressure. And this causes much of the physiological changes, compensations, and even damages to our bodies. And from Pendergast 2013, he describes these a series of changes within the cardio, respiratory, and renal systems. So we have a change in the systemic system, heart, cardio systems, respiratory systems in the lungs, and the renal system. So we have a change in basically a influx of the fluids of our body. So like I said, the significant results are seen beyond the depth of 2 atmospheres or 33 feet. And temperature is also going to play a role in the physiological changes and adaptations below 25 degrees. And just to point out, many of the dangers of scuba diving, recreational scuba diving, don't come from marine life. They actually come from the drastic changes and time that we spend with pressures from pulmonary embolisms, which is air getting into the bloodstream and traveling to our brain, usually a result of a cause of death. Minor injuries, such as the next picture here, where the capillaries in the eye have burst due to a rapid change in pressure, and some extreme cases, like we see with the medevac team, transporting a patient in a portable hyperbaric chamber. So understanding pressures, we can understand what I research what changes happen during at depth. So at depth, our breathing is also going to change. Breathing under pressure, hydrostatic loading is how we describe the pressure on the pulmonary system. And we see a decrease in pulmonary compliance overall, a decrease in the efficiency, respiratory efficiency of about 49%, and a decrease in inspiratory power of about 26%. Now what does this mean for us? Well, it means that our muscles of the body are going to have to work a little harder to breathe normally. What happens in the lungs? What happens in the lungs under pressure is that the dead space in our lungs, the space beyond the alveoli, the space that doesn't have diffusion happening, the change and exchange of gases, is called dead space. And so that increases, decreasing the amount of air traveling to the alveoli. Not to the extent that breathing is impossible, but to the extent that a hypoxic environment may be accumulated. So we see in this picture a technique in which somebody can be comfortable in breathing inside of a microenvironment, this exoskeleton, for very, very deep dives, at which point the human body could not survive. So let's talk about gas densities. Like I said, gas densities at 1 atmosphere are kept at a normal range due to that 1 meter squared column of air that in combination with gravitational force. And we see a resistance to the airway due to these gas densities as well. Resistance to the airway of up to 42% overall, a drop in ventilatory threshold of about 18%, and even our breathing frequency of about 20%. But the affinity for diffusion is most important at depth. Ambient air is about 21% oxygen and 79% nitrogen, or all of the other gases in the atmosphere. But under pressure, the gas that our bodies produce, the carbon dioxide, under pressure, it has a greater affinity greater affinity to diffuse into liquid than oxygen does. So therefore, blocking oxygen a little bit and creating this hypoxic condition. Now let's look at heart rate. The change in heart rate is directly affected by the pressure, baroreceptors picking up the pressure, changing the physiology of the body, and in the pressure also changing another part of the systemic system by vasoconstricting. So heart rate in particular, due to the pressure change, the body experiences a sustained bradycardia, or a sustained low heart rate compared to a resting heart rate. And this is measured with heart rate variability, the distance between the R waves on an ECG. And of course, this is a non-invasive measure using either an ECG, a Doppler, or an ultrasound. And we see a reduced heart rate of about 9.72%. So I mentioned vasoconstriction. Vasoconstriction is affected by another variable, and that's temperature. As a recreational scuba diver does descend into the water, he or she may hit what is called a thermocline. And a thermocline is a band of water where a rapid decrease in temperature exists. So we have this top band of warm water, a lower band of very cold water, and in between we have what is called a thermocline, this rapid decrease in temperature that separates those two bands of water. Now, a recreational scuba diver, depending on the depth at which he or she is diving at, may experience 1, 2, or even more thermoclines. I can say from experience, I reached a thermocline in Cayuga Lake at about 45 feet. But when the human body is exposed to cold temperatures, there are receptors, especially on the face and on other parts of the body, that tells the body, okay, we need to slow down, temperatures are getting colder, and the body naturally vasoconstricts the peripheral areas of the body, the arms and legs, and pushes the blood towards the thoracic region of the body. And this is the same thing with the pressure. Pressure also does the same, putting pressure on the arms and legs and vasoconstricting and pushing the blood towards the lungs and the heart. But let's compare what we see with immersion versus submersion. A study also by Pendergast, 2013, made this comparison that with immersion, head out of water activity, there exists an increased heart rate, an increased stroke volume, and so therefore an increased cardiac output, which is a product of heart rate and stroke volume. But during submersion, as we've gone over so far, we have a decreased heart rate, no change in stroke volume, and therefore we have still a decreased cardiac output as the product of those two. So in summary of these concepts, the pulmonary system does see an overall decrease due to the resistance from pressure, gas densities, and the scuba regulator. Cardiac changes, we have a slowing of the heart rate, and temperature slows down the systems as well, and with the blood flow vasoconstricting the peripheral aspects of the body and pushing the blood towards the thoracic region. Now, that's one thing we didn't touch on yet is the renal system. Now, as the blood is pushed towards the thoracic region of the body, viscosity increases and blood plasma also increases, regulating the blood pressure. Now, some of the delimitations of this experiment, it was interesting to find that many of the participants in many of the studies were well above or in their 20s, having recent diving experience, and many as experienced military divers. So this leads to some limitations to the studies, as in what kind of age group can we look at to share this information, to have this information actually viable to the aspect of scuba diving. So because we've only seen participants in their late 20s up to about their mid 40s. So what does this mean for young people? What does it mean for old people? And many of these studies, many of these studies were non-invasive. Some were invasive, measuring very particular aspects of the systemic system, but really to an extent where the results were negligible. Many of the studies themselves really didn't exceed about 10 participants per study, and used, and the majority of them used hyperbaric chambers with either in a dry setting or with a pool of water inside to simulate an active submersion, either at rest or during physical activity. And the difference between those two, we still see the same kind of outcomes from a control to the experiment. Physical activity to physical activity, you still see a reduced heart rate, peripheral resistance, and a reduced cardiac output. And even during rest, within these hyperbaric environments, either in dry or in a wet environment, at rest we still see those same changes.